Hello. I have a short video, hopefully short here, about justification of Euler's formula. Euler's formula is e to the it equals cos t plus I sine t, where t is a real number and I is the imaginary unit. I squared is -1. All right. But I'm going to do this using ODEs. Cool. All right. First thing I want to do is do an equivalent of this. If I do e to the minus it, this is going to be cos of -t plus I sine of -t. The cos is even, and sine is odd. Right? So that's what e to the minus it is. If I add them, I get e to the it plus e to the minus it. That's 2 cos t. And I subtract them, I get e to the it minus e to the minus it is equal to 2I sine of t. Right? If I add these, those cancel. If I subtract them, those cancel, and that doubles. Okay? So in other words, I really got a formula for cosine of t is equal to e to the it plus e to the minus it over 2. And formula for sine t is e to the it minus e to the minus it over 2I. Just a little aside here. I'll do it in some color, say orange. The hyperbolic cos, I like to say, cos of t is, remember that this is e to the t plus e to the minus t over 2. And sinh, or hyperbolic sine of t, is e to the t minus e to the minus t over 2. No i's there, no i's anywhere in this formula. Okay. And while we're at it, that means that cos of it is cosine of t. If I replace t by it, I get this formula. And what do I get here? If I replace sinh of it, I get e to the it. I get almost that. I get I. Okay. Let me see. What do I get? I get e to the it minus e to the minus it over 2. I don't have the I in there. Okay. So it is, to multiply, it's equal to I times sine of t. Right? Because what I get from here, okay, is this whole thing without the I. Okay. Sine t is that. Okay. I'm not sure if the I is on top or the bottom, but all right. But that's an aside anyway. All right, so let's see if we can prove this. So what I'm really going to be proving is this. I'll write these formulas up here. That cos of t is this one here, e to the it plus e to minus it over 2, and sine of t is e to the it minus e to the minus it over 2. All right. And as I've said, well, maybe I've said it, maybe you haven't heard me say it. But often this formula is justified with Taylor's series. But I'm doing it a slightly different way here. So what I'm going to do is think about, consider y double prime plus y equals 0. All right. And I need to have a little bit more room here. You have the IVP, y double prime, okay, plus y equals 0. Y of 0 is 1. Y prime of 0 equals 0. And I'm going to do another one later. But let's just do this one. All right, well, Well, by inspection, y of t equals cos t is a solution. Well, because y prime is going to be minus cos t. Y double prime is derivative of, y prime is minus sine t. The derivative of sine is cosine, so I have minus cosine of t. That's, yeah, the original y is cos t, so y double prime equals minus y. In other words, it solves a differential equation. It solves the initial condition. Y of 0 is 1, y prime of 0 is 0. So it is the one and only solution. It can be written in billions of different ways, but this is the one and only solution to that initial value problem. Okay? So let's do it this way. We have r squared plus 1 is 0. So r squared is negative 1. R is plus or minus I. So y is c1 e to the it plus c2 e to the minus it is also the general solution, but now it's complex value. Let's take y prime of t. It's going to be I c1 e to the it minus I c2 e to the minus it. All right, so let us solve the initial value problem using this. Y of 0 is c1 plus c2. Y prime of 0 is I c1 minus I c2. And now c1 and c2 might be complex numbers. And I'm going to set this equal to 1, and I'm going to set this equal to 0, and solve this system of two equations in the two unknowns c1 and c2. Okay. Oh, this is kind of easy. c1 equals I c2, therefore c1 equals c2, but they add up to 1, so they're half. So that means that y is a half e to the it plus negative a half e to the minus it, also written as, let's write it this way, e to the it equals e to the it plus e, they're both plus a half. Okay. So the one and only solution to this initial value problem can be written as cos t. It can also be written as e to the it plus e to the minus it over 2. Bingo, I've got that formula. Right? It's uniqueness of solutions. Cool, let's do the other one. Suppose I want to solve the other guy. These two sets of initial conditions are the uber important ones that we like to do sometimes to find a nice solution set, right? The most beautiful fundamental solution set has these two sets of initial conditions. Let's do this one. Oh, this guy has a solution sine of t. Y of t equals sine of t is by inspection the solution to this new initial value problem, right? The second derivative of sine is negative sine, so it satisfies this. Satisfies y of 0 is 0, yeah. Y prime is cos t, cos of 0 is 1. Cool. All right, now let's solve this initial value problem using the formula c1 e to the it plus c2 e to the minus it. Well, it's the same thing. I probably shouldn't have erased it. All right, so that means that y of 0 is c1 plus c2. this is all the same as we had before. Y prime of 0 is I C1 minus I C2. So that's all the same, but now we're setting y of 0 to be 0 and y prime of 0 to be 1. So now I've got to solve this system of two equations in two complex unknowns, C1 and C2. We do the same thing, right? C2 is negative C1, almost the same thing. Plug that into here. I get I C1 minus I. Oh, C2 is negative C1, and that's going to be 1. In other words, 2I C1 is equal to 1. C1 is 1 over 2I. And C2 is negative that. C2 is negative. I'm running out of room. I got that. So C2 is negative 1 over 2I. So I put those together, and the solution to this guy here is one way of writing the solution is sine of t by inspection. By solving this for C1 and C2, I get C1 is 1 over 2I. C2 is negative 1 over 2I. I need the negative sign here. And I've got the second formula. This formula. The one and only unique solution to this initial value problem can be written as sine t. It can also be written that way if you want. And by the way, the fact that it can be written that way is why some of your web work problems say, make sure you don't use complex numbers, because web work can't analyze complex numbers. All of those problems that have complex roots of the characteristic equation, you can solve them for the normal way with C1 and C2, writing it something like that, and then C1 and C2 are going to be complex constants. You don't want to do that, but you could, and you get something like getting this as your solution with the i's in it, but web work will say, I don't know I. I is not my friend. I'm not my own friend. Yeah, okay. All right, so yeah, like I say, there's a standard way with Taylor series, which are pretty awesome as well, but that you'll see in a lot of places. But this is maybe a little bit different. It's not, of course, unique to me, but all right, so I think I'm gonna stop this marathon of Tuesday morning videos that I'm making to fill in the parts of the course that I don't have time to do. All right, so bye.